Imagine building a precise robotic arm or designing an aircraft's autopilot. What would happen if a subtle command caused violent shaking or runaway behavior instead of smooth motion? Understanding the conditions that lead to such instability is paramount for any control system. Gain margin and phase margin are essential stability criteria because they provide quantitative measures of how robustly stable a feedback control system is. These metrics predict how close a system is to oscillation or divergence, ensuring its predictable and reliable operation. The core mechanism behind their importance lies in the nature of feedback loops. Instability often arises when a system's output feeds back into its input with the wrong phase, causing positive reinforcement, or when the gain around the loop is too high, leading to uncontrolled growth. Gain margin tells us how much the system's gain can increase before it becomes unstable at the frequency where the phase shift is exactly 180 degrees. A system becomes unstable if its gain exceeds unity, or 0 decibels, at this critical phase. Similarly, phase margin indicates how much additional phase lag the system can tolerate before instability occurs at the frequency where the loop gain is precisely unity. Insufficient phase margin means the system lacks the necessary damping to settle quickly, often leading to undesirable oscillations. Engineers use these margins to design and tune controllers, ensuring that the system operates from the brink of instability. For example, a robustly stable system will typically have a gain margin of at least 6 decibels and a phase margin of at least 30 degrees. These values are determined from the open-loop frequency response, often visualized on Bode or Nyquist plots. Adjusting controller parameters, such as proportional, integral, or derivative gains, directly impacts these margins, allowing engineers to balance stability with desired performance characteristics like speed of response and accuracy. What makes these margins particularly powerful is their direct connection to the Nyquist stability criterion, which graphically identifies potential instabilities. They offer a practical way to assess a system's resilience without needing to solve complex, closed-loop characteristic equations every time. By providing a clear safety margin, they guide the design process, preventing costly and dangerous operational failures. Ultimately, gain margin and phase margin are not just theoretical constructs. They are indispensable tools that quantify a system's capacity to handle disturbances and parameter variations without losing control. By carefully considering these margins, engineers can confidently design systems that are not only stable but also perform reliably and predictably under various operating conditions, preventing unexpected and potentially catastrophic behaviors.